Martha, I think you can start.
Okay, perfect.
And since this time, unfortunately, I have to attend the faculty meeting, I may not be able to stay, but others will. But I check out the recording afterwards. Thanks.
Sure, sounds good. Thank you very much. So, hello everybody. Thank you very much for joining. Today I'm going to talk about this paper by computer scientists at MIT, which is regarding causal navigation by continuous time neural networks. They developed a new method that employs causality to be used in drones and visual processing, and it also has applications in other domains as well, as long as a few assumptions are met, and we're going to talk about them in more detail. So basically, what they are proposing is that they are proposing a new method called neural circuit policy, and this method is, as I said, is employed in drones to track objects and identify objects, but it is using causal inference, continuous time causal inference, and this method has performed much better than other neural networks that are out there, and it is basically some sort of state of the art. And as we see in this figure, the drone has been given a moving object, this red dot, as we see on the screen, and different models have been used to track this object. We have neural circuit policy, which is the subject of this paper. We have ordinal differential equations recurrent neural network, being also performing, but a lot poorer than this causal structure, and long short-term memory, and also continuous time gated recurrent units. As we see, for example, for LSTM that usually performs very well, it could not isolate these moving objects as well as this causal neural model did. It got distracted by light and other things in the environment. Also, same thing with ODE RNN and CTGRU. And then in this paper, we want to go through why this method is better than the rest of them and how causal structure has been used to perform this high efficiency. So before we get started, there are different terminologies and different terms used in the paper, which I want to address before we dive deeper. You may already be familiar with some of them, but it's a good refresher before we dive into equations and algorithms and things like that. The first thing is that this paper, Causal Navigation by Continuous Time Neural Networks, is based on another paper from the same group, which they published, I think, in 2021. And there they explain fully what liquid time constant networks are. And this is more of a theoretical paper. And what we're going to talk about today is that the application in the drone industry. So for more information about this paper, you can find more information here. But I just wanted to mention that more theoretical details can be found in this group's prior paper that they published last year. And there are some concepts that are good to know about, which I'm going to touch upon them real quick before we dive much deeper. The first thing is the difference between imitation learning and reinforcement learning. What is imitation learning and why they are using it in this paper? Imitation learning is where a machine is imitating human behavior instead of having direct interactions with the human. For example, in reinforcement learning, an agent and the system are interacting with one another, and the system gets rewarded for every time they perform the task successfully. But in imitation learning, the machine is trying to imitate the human behavior without direct interactions with the human. And that's what they are doing in this case. They are using the drone as an example to have an autonomous system instead of having reinforcement learning. So that is the first concept, imitation learning, they're using in this paper. Another concept is discrete time neural networks is discussed in this paper. The subject of this paper is continuous time neural networks. So I thought I would mention the difference between continuous time and discrete time. The discrete time is when we have a neural network system over time, but time is not measured continuously. We have different time points. We have t equal 1 second, 2 second, and more is at discrete intervals. Whereas in continuous time neural networks, in this example, we see, for example, if x-axis would be time, we have a continuous sort of results for training data. And this is what is used in this paper. They're using continuous time neural networks. Data is measured through time without any interruptions. And that's the case of drones. When it's taking video or when it's looking at the environment, it is continuous time. So that is another concept. Another one is causal representation. What causal representation is, in short, it's either of these three representations are causal representations. It's where we have a treatment and we want to see what causal effect it has on an outcome. It can have different forms. It can be as simple as the first one. It can be more complicated, and it can have impact on basically different effects as well. We have a treatment, and then we have an intervention, and that treatment is part of that intervention, and then it has effect on a variety of things. And this is discussed in more detail in the paper. Just wanted to show an example of causal representation. Next thing that is discussed in the paper is saliency maps that they use to, we just looked at them. These are saliency maps. They are used in basically in artificial intelligence and computer vision to identify objects, or basically locate what, as they say, what a human being would look at first when they are given an object. So it's sort of maps that is very informative to kind of track objects and find objects in a picture or in a video. Trying to move on to the next tab here. Another thing they talk about in this paper is neural circuit policies, and I'm going to discuss this in a little bit more detail, what neural circuit policy is. But what it is it is a neural network that causal structure has been applied to it. We have directed graphs and indirected graphs. We have directed edges and indirected edges, which show causality between the nodes and different variables in the graph. This is another example of NCP networks within the structure of liquid time constant neural models. We see that neural circuit policy, or NCP, we have it guides the flow of information in a neural network through causality and through causal models. Then there is differential equations or ordinal differential equations. There's a good example of it here, comparing an RNN encoder or recurrent neural network encoder with ordinal differential equation solver. They sort of operate the same through time. The information is provided to the system, and then we solve that. Basically, we use a differential equation solver to solve for different parameters and variables in the system. We also have time from T0 to Tm, which is also part of this ODE solver. Instead, whereas in an RNN model, we have a different equation and different sort of sigmoid or different functions that are used. So in this paper, they use differential equation solver in order to solve the neural network in forward and back propagations. And there's another term used in the paper called LSTM, and we see the model here as well. It's short for long short-term memory. It's a type of a recurrent neural network that uses channels in order to basically train the data through different channels, and there are inputs and outputs, and there are cells within the RNN that can provide information for training. There's also GRU that they use in this paper, which is this last model that we have, continuous time GRU, and GRU stands for gated recurrent unit, which is a type of LSTM, but it's the newer version of it, and it's been used only in the past few years. It's very similar to LSTM, but it does not have the cell, and the cells are not connected to one another. The flow of information comes in and gets out without the cell, and because it does not have the cell, it can be trained faster. So it has that advantage to be used. And this is that example I was talking about, differences between LSTM and GRU. And throughout the paper, we can come back to these tabs and different parts of the basically terminology to gain more insights. So there are 4 models used. One is neural circuit policy. Another one is differential equation recurrent neural network, LSTM, and gated recurrent unit that they are using to prove basically that their model operates better. Next in the paper, they talk about the causal navigation from raw visual inputs. They explain how they are using causality and how they're using causal models to train their neural network in their time continuous neural network. And first they talk about different type of models that we can have in the nature and in statistics. The most complete type of model they describe is physical model. For example, a physical equation, F equal ma, for example, that satisfies all this criteria. It gives us insight about the system. It learns from the data. It answers counterfactual questions, predicts in IID, and also it responds very well with interventions. Then we have structural causal models that satisfies almost all of them, with the exception of insights about the system. It does not provide that insight as a physical model does. And then we have causal graphs that does not answer counterfactual questions. It just provides insights about interventions. Whenever we have interventions, we can infer causality, but we cannot answer counterfactual questions. And then there are statistical models that only can predict in IID and also learn from the data. We cannot have any interventions, or they cannot give us insight about the system or answer counterfactual questions. In this paper, what they basically use is structural causal models, because they also talk about counterfactuals and different directions in causality as well. And they have a lot of references to very good works by Perl and Spitzer and Scholkopf, and these are very knowledgeable people in the causal structural models, and they have provided very good insights in this field as well. So they sort of use what is available to them in structural causal models to apply that in a neural network context, and then they show they perform experiments and show results consequently. And then they talk about how continuous time neural networks can be causal models. They show that by equations, how they can establish that connection, which we're going to talk about in a second. So in order to get us started, they have some very good references here to what causal learning is. They have very good papers provided, and very good references to good articles in this field. And then they talk about what continuous time models are, which as we mentioned, it is they are models that we have temporal data or time-related data without any interruption. They are continuous time, and they provide list of papers that have used continuous time models as well. And then they also talk about imitation learning and what it is, and very good sort of publications regarding imitation learning. And they also talk about visual navigation and what work has been done in visual navigation world. One thing that is important to note about this work is that they use um, a causal navigation in continuous time neural networks. And as we see, it operates better than other models. And one reason they mention that this operates better is that they are performing these experiments in closed form versus in open form. And what I mean by that is that in an open form, for example, let's say we have a drone and we send that drone into environment to capture objects or identify objects, as these 3 models usually do, but they usually have interactions with a human agent, with a person, with a real person, and this is called open um, form of learning. But in these experiments, this is closed form, meaning there is no interaction between the system and the real human being. So there is the system has to learn on its own the environment and what they what the task is and what they want to accomplish based on the environment. This is why causal modeling is helping here, because there's no human involvement, and this because this is in closed form, this sort of model or method is being very helpful. Hence, they are using causality to establish that. So this is a closed form sort of experiment that they performed for computer vision and visual navigation. Then they talk about the problem setup. They talk about causal structures, how causal structures can be established in such a case. There is a concept called structural causal model, or SCM, developed mostly by Pearl and Spitzer and other people, which talks about in a causal structure, we can have in a causal graph, we can have different variables as the vertices of a graph, and that graph is usually directed acyclic graph, or DAG for short. And then the edges in that graph are relationships between those vertices or those random variables. If they are directed, it is inferred that there is causality between those vertices, and if it is indirected, means there's no causality. If there are more information in the publications they provided here, but in short, they want to talk about structural causal models that has been used. What is important here is the concept of interventions, and how they are using interventions in this research is that they're saying that let's say in case of a drone looking at the environment, all the information that the drone is getting over time, because there are different inputs about the environment. They are getting so many different inputs. One is time, one is environment. They can there's a lot of information in the pixels of the pictures as well. They are considering different environments and different variables in the environment as interventions, compared to, for example, 10 seconds ago, if a drone starts from a location, point A, and goes to point B, they are being sort of exposed to different environmental variables, and they are considering those variables as interventions compared to 10 seconds or a few seconds before that. So they are establishing causality based on this type of intervention, and they have the time variable as well. So that's how they're using causality or causal learning in their research. And then if they can establish causality, there are sort of conditions and assumptions that needs to be met, which we're going to talk about in a second. But if they can do that, they can confidently say there is a causal relationship between 2 variables or more variables in their data. Then after talking about causal structures and what they are, they talk about differential equations. which can form causal structures. This is not always true. Not every differential equation can form causal structure. There are assumptions that need to be met, which they talk about as well. Differential equation has been extremely useful. One example I wanted to show regarding differential equation has been the Schrodinger equation, which is a sort of a differential equation as well. And this equation has won a Nobel Prize in physics. A lot of different phenomena can be used using differential equation, especially when we have time, and we do have time in quantum mechanics. This can be very useful to sort of establish the relationship between time and space, or time and another variable. In this case, in this paper, time and environmental variables. Differential equations are very useful. And if we can establish relationship between differential equations and causal structures, we can have a causal model that can be solved using differential equations. And what they do is they start with a simple example with this, the most simple equation in differential equation is the the derivative of space and time, which is a function which is called speed usually. But let's say we have a derivative of x with respect to t, and that is a function equal to g of x, and where g is a nonlinear function. Then they talk about a theorem, Picard-Lindolf theorem, that states that an equation that is in this form has one unique solution. It has only one unique solution if g, this function, is Lipschitz or Lipschitz. And we're going to talk about what they are and what they mean. But very briefly, I wanted to sort of explain what Lipschitz functions are. It's very similar to continuous functions, but how they're defined is that if alongside our function we have two white cones like this, if we see in this picture, if these two white cones intersect on our function, at no point will any part of our function have basically intersection with either of these two white cones. And this is how Lipschitz assumption or function is being established. There is a lot more to it. You can learn more about it, but it's a very special case of continuous functions. So what they are saying here is, in this differential equation, we can, if this function g, if we can prove that this is Lipschitz continuous, as we just described, then we can say this differential equation has only one unique solution. And this really helps with establishing causality when we get to neural network subsequently in the paper. And then they use the Euler method to unroll this very equation into infinitesimal differential, and they add the time variable as basically they sort of expand it using the Euler method, and they come up with a new function called f, and they say this representation, if we can prove that has only one unique solution near future events of x, we can, based on the past information, because we have time a variable here as well, if we can establish that in the near future or locally this equation has one unique solution based on the past information or training data, we can say that this is forming a causal structure. And they talk about this a little bit more, but this is the idea and this is the concept, which is very helpful, combining differential equations with Lipschitz function and expanding it using the Euler method. Then they talk about structural causal models, how they process the effects in a system that we have interventions, which they talk about more in the rest of the paper. Then after talking about what causal structures are and how differential equations can be a form of causal structures, they talk about neural networks and how time continuous neural networks can be formed as causal models using the two concepts they talked about over here and over here. So in a particular neural network, usually there is an activation function that is used and also there is a loss function that is used for forward and backward propagation. It's they usually do not use differential equations in neural networks, but in this case they do, and their differential equation has time as one of the parameters, and that's how they establish causality in a neural network. A very important paper that they list here is this paper from Funahashi and Nakamura from 1993, where over here the concept of continuous ordinary differential equations in deep learning has been established and has been sort of proposed, but has not really been employed, and the application has not been used. But they sort of get the idea from here, but they sort of expand it as well. And then they talk about the concept of using a hidden state in their neural network, and a function f, as we see over here, which is establishes a differential equation to calculate this f, to establish this f function based on the hidden state in a neural network. And they also reference this paper from Chen et al. From 2018, and this f function, which is basically computes the solution to this hidden state of the neural network, has a parameter theta as well as a t parameter, t being the time, because we're working in continuous time, and theta is parameter that has all the information that is being received from the environment. They expand this theta as well into other matrices in the other parts of the paper. And then they talk about approximating and expanding this very simple equation, which talks about hidden state of a neural network and its connection to differential equations by adding another term to this equation, which is a function of the hidden state divided by a time constant tau, and they add that to their equation as well to sort of to increase basically to achieve stability, as they say in the paper, and to make the equations performed in a much smoother manner. They also take one step further to, as they say, increase expressivity, and they make this a liquid time constant network with this following representation. So far in these two equations, equations 3 and 4, they've been talking about time continuous neural networks, but in this form, they now use the term liquid time constant, and they have a paper as I reference here, which is the bedrock of this paper. They talk about what liquid time constant networks are, and in a nutshell, what they are is that they are neural networks that employ differential equations, and they are time continuous, and differential equations are used in forward propagation and back propagation. So it's like a they call it a liquid, sort of in both directions. It goes both ways, and it is being integrated in both ways. So if you want to learn more about liquid time constant networks, they have another paper as we listed here. And then this is the equation for that liquid time constant. This is derived from this other paper, which is a more theoretical paper than this one. And then they talk about introducing output controlled bias vector and using a Hadamard product here as well. So this was an overview of the theory. just to recap, they talk about causal structures, differential equations, and time continuous neural networks. Then they talk about the results, how they use these three concepts to come up with a new theory and a new idea to establish causality and causal modeling. And what they start with is they start with an equation very similar to what they have, than what they established above over here. They start with this equation, which is a differential equation, and they say this is usually this is not a form of causal structures, even if this function f is Lipschitz continuous. So they talk about different assumptions that needs to be established other than f being a Lipschitz continuous for causality to be established. And they talk about another theorem called Picard-Lindahl theorem that should also be used. It's a Picard-Lindahl existence theorem that is used in couple with Lipschitz continuous, that, as we see here, to establish causality. And I actually have that here as well, if I can find it. Picard-Lindahl theorem is a theorem that says, in a nutshell, that another name for it is the uniqueness theorem. Gives a set of conditions under which an initial value problem has a unique solution. So what this on theory does is that it provides some assumptions and different conditions that, if they are met, we can say that a particular function, or in this case a differential equation, has only one unique solution. And using that coupled with the Lipschitz continuous assumption, they can establish causality, and they actually prove that in the paper. So they say, if you start with this differential equation, if f is Lipschitz continuous and this theory holds, then we can establish causality. They talk about using maximum likelihood estimation and using statistical methods to predict IID. But if they want to establish causality, they need to have other assumptions available. That's why they come to this section of the paper. They talk about liquid time continuous neural networks, which are dynamic causal models. And this is another paper that they reference here, which is by Friston et al. 2003 paper, which says liquid time constant and neural networks. And this is the sort of the equation for the hidden layer of this neural network differential equation. This is a type of dynamic causal models, and the definition for dynamic causal models is presented in this paper. And they say a bilinear Taylor approximation of dynamic causal models can be a liquid time continuous neural network. And then they talk about how it can be derived using equation. They use an equation similar to what is used over here, but they change the names and change the terms in order to construct three matrices. And using those matrices, they want to prove their functions. And what they say is that for a given system, such as differential of x with respect to t, if we can have a function, a capital F, that is a function of a hidden state for neural network x of t, and if we introduce a new function called I of t and theta, we can have this and establish this differential equation. They talk about assumptions. And just to briefly explain what these are, is that this is a differential equation as we see over here, but this I function, which is a function of time, is all the inputs that a system receives. All the inputs from the environments that the system receives is captured in this I function, which is a function of time. And in order to solve this sort of equation, if two assumptions are met, then causality can be established. And then they have made the function a little bit simpler by assigning different derivations to these values. A is the first derivation of this function f with respect to the hidden state x, and then b is the second derivative, or it is, as it's mentioned, bilinear Taylor. It's a bilinear approximation, or second order approximation with respect to all the inputs that a system receives, and also a hidden state of the neural network. And then also C is a derivation of that function f with respect to all the inputs a system receives. I being the inputs to the system, and X is the node's hidden state. So this is the relationship between hidden states in neural network and the information flow of information that a system receives. Then they talk about what the role of these each of these matrices are. They talk about matrix A having all the fixed internal coupling of the system, because we're not taking the derivative with respect to this function I of t. This is going to be only internal, and we're equaling I to 0. So this is going to be all internal for the system. Matrix B is going to control the impact of inputs on the coupling sensitivity among networks nodes. And as we see here, we are taking derivative of this f function with respect to both hidden state and the inputs that a system receives. So this is going to be coupling sensitivity among network nodes, or controlling internal interventions. And then this matrix C, they talk about, embodies the external inputs or influence that the system receives, which is the external information, or controlling external interventions, because this is they want to establish causality. That's why they use intervention language. Then they talk about a proposition, which is, they say, if this function, if a function f is a nonlinear, is the nonlinearity of a given liquid time continuous network, as we saw in equation 5 over here, which is the LTC, or liquid time continuous network, then the learning system identified by equation 5 can account for internal and external interventions. And when we say interventions, we're talking about causality, as we saw in this. It was in one of the tabs. As we saw here, we have a treatment and an outcome. We have intervention. While its weight parameters theta, and theta has been captured in this equation, as we see over here. We have theta in equation 5 in the liquid time continuous network, and I think I passed that. For the cells and the input size m, and A being this matrix, therefore forms a dynamical causal model if f is Lipschitz continuous. And then they also provide the proof here. To prove this, they say they need to show two properties for LTC networks, and the two properties are, one is the uniqueness of the solution. They need to show that that the equation they create here has only one solution, has one unique solution. And also the second condition they mention is existence of intervention coefficients. There needs to be intervention coefficients to establish causality. And for the uniqueness, they talk about this Picard-Lindahl theorem that we showed over here, that there are assumptions that for a differential equation can, in that case, we can say there should be only one unique answer. And then they reference some paper and say it has previously been shown that for a function f that meets these conditions, then they sort of prove using this equation that there is only one unique solution on 0 to infinity. And then they provide proof in this other paper as well. Then the second condition is intervention coefficients. there needs to be interventions. What they talk about is that if function f is a Lipschitz continuous activation function, such as hyperbolic tangent, which is a Lipschitz continuous function, which meets this criteria, then they say if they set x to 0, then they set x to 0 because they want to focus on external intervention and not internal, because x is the hidden layer of a neural network. If we set x to 0, we're focusing on external interventions, and if we do that, the derivative of the f function over all the inputs, if x is equal to 0, would take this form based on equation 7 that we have over here. And then they say corresponding internal intervention coefficients b of equation 7 for liquid time continuous networks becomes this. And what they did here is that they first set x to 0, then they calculated the derivative for f with respect to external information, which has this form. And what they did was they recalculated equation 7 using what they got here in order to calculate the whole sort of derivative in matrix B, which is the derivative of f with respect to x and also function I. And they do that based on what they got up here. And they say this shows that by manipulating matrices W and WR, which are the weights for I and X and A, one can control internal and external interventions to an LTC system. And what they're saying is that they are manipulating and controlling basically the coefficients that they have in their differential equation, and they can control for internal and external interventions. And continuously, they say that because in proposition 1 over here, what they could was they showed that LTCs are causal models in their forward pass. They established this by satisfying these two assumptions, uniqueness and existence of intervention coefficients, because it is being causal model in forward pass. By manipulating the parameters, one can gain insights into underlying systems. Then they talk about in the backward pass, in the back propagation of the neural network, they can also get a causal model. And they also show that in this paper as well, that a core finding of their paper is that the model they train from reverse mode auto differentiation also gives rise to a causal model. And this is where the Lipschitz and the Picard-Lindahl theorem helps them in establishing that their model is causal in forward and also backward. So after talking about establishing causality and saying that liquid time current neural network are also dynamic causal models, they talk about how they train it on a basically in neural network, and how they calculate the loss. And they say they're using gradient descent that also yields causal models. And L here is the loss function for this neural network, and the loss function in it includes an integral of a differential equation, and as we saw, it has only one unique solution. Then they talk about more details how solving this loss function can also contribute to establishing causality. After they talk about all the theoretical stuff, they move on to experiments and real world implications. And as I said, they talk about they're performing this in a closed loop environment without any human interactions. That's why their system is beating other system. Then they perform some experiments, and in their experiments, they have actually 3 types of experiments. In the first type, they have a static object that their target is static. It's just placed in an environment, and they have their drone looking for that object. They want to see how it can capture it. Then another type of experimentation they do is there is a moving object and the drone is following that object. What they want to see if the drone, and this is the image that the drone sees. And the third type is a hiking sort of path that on each tree there are some signs, and the drone kind of follows that object basically through the trees. And then they provide sort of results on how the model performed. They have neural circuit policy, which is the same thing as the liquid time continuous neural network. And as we see, the red object can be seen by the drone with high accuracy. Other models could, in some cases, identify it, but light and other environmental variables have been perturbing the outcome. LSTM and GRU also did not perform that well. And then they report their the outcomes in a table like this, and using cosine similarity loss. And this the smaller the cosine similarity, the better. So NCP model that they trained operated better in redwood forest environment when they compared them for short-term navigation. And then they performed another experiment with moving targets. When the target was moving and it was in motion, they also see that their model performs better in neighborhood environments. And also this table is using cosine similarity loss. The table on the left and the table on the right is sine similarity loss. And they see that in the moving sort of environments, their model only performed well in neighborhood and not in the forest and other environments. They provide the results here. And then they have another sort of experiment for hiking through an environment. And what they observed was that for different methods, the drone got too close to the object. And as we see here, the drone got very close to the objects. But in this case, in this causal model, it maintained the distance and correctly was able to identify where object is. So it was maintaining the distance and also identified the location of the objects, sort of beating other models in accuracy. And then they provide the results here. They also performed experiment on in different environments when the sky was clear, or it was foggy, or there was light rain, heavy rain, or there was occlusion. And in most of the scenarios, if we had a static target and their model beat other models, same thing for chasing with some exceptions, and also in the case of hiking. And after they provide the results, they actually have the image of clear sky, raining, and foggy in environment. Then they talk about conclusions. There are 3 advantages to this method. Actually, there are a few. One is that model performances drop significantly when we have a closed loop environment, meaning no human interaction, because in those cases the system has to figure out on its own what to navigate and what to do. Here's where causality helps, and also robustness to environmental perturbation, meaning when it is foggy or rainy, other models perform much worse. But this model, even in different environments, performs still very good. So from a clear weather to fog, we have the performance here is 48, but for foggy drops only 8%. For heavy rain, we have better performance even, so the performance is very robust to environmental perturbation. And then they talk about why they use recurrent neural networks and why not temporal convolutions or attention-based models. And then they explain why they did that and how they can handle occlusions and temporal dependencies using what they have, and because they're using differential equations. And then they talk about how this can be coupled in the future with recurrent neural networks to get better results. And then at the end, they show the spatial presentation of continuous time models realizing causal models and how they can significantly enhance decision making in real world application. Before I stop, very quickly for questions, one thing I want to mention is that a lot of our research may not be directly related to this, but where this can be helpful, or this sort of a model causal neural network can be helpful, is where we have high dimensional data, because what they had here, the drone is looking at the environment in a very high quality, and there's a lot of pixel data. So this is a very high dimensional data. So if in our own research we have high dimensionality, this is a good case to use this type of analysis. And also where we have temporal data, when we have time continuous data, time series with a lot of data points for time, we can also use this model, because in the differential equation they factor in time as well. So the last sort of situation we can use this type of analysis is where we don't want to, in the training process, we want it to be a closed loop. We don't want to have interaction with the system. We don't want to have a reinforcement learning. We want the system to on its own figure out the environment. These are the different scenarios we can use basically this causal analysis for continuous time neural networks. I know we're at time, and I'll pause now if there are any questions or comments, and really appreciate you guys listening.
Hi, Morteza.
Hey.
Thanks for your presentation. It was really very good. I have two questions, if possible.
Sure.
One is about overfitting. How we can get sure that our model doesn't get overfit to our data?
I think that's a very good question. In this paper, they did not provide answers to this type of questions, but in general, in order to avoid overfitting, maybe usually the training data set and the validation and test data set, that maybe you can try different sizes for your training data and test data and like validation data. If you're not using cross validation, maybe that's a method to kind of improve that, making sure that your models do not overfit to your training data. Maybe obtaining more data to have more variance in your training data, so it would not overfit to just one particular pattern. But I would say focusing more on the sizes and employing cross validation as well. These two things I can mention.
Okay, thanks. My other question is about, I would like to know how causality affects the computational complexity of deep neural networks.
Yeah, I think that's a great question, and I think it might make it more complicated, because instead of a simple activation function, we are using differential equations. So this is definitely making it more computationally expensive. But the point of this paper was to provide a state-of-the-art sort of algorithm to have higher accuracy. But I think it makes your computation more expensive for sure.
Okay, thank you very much. Thanks.
Sure. Yeah, you're welcome. Thank you. And the recording will be, I think, maybe provided after the meeting. And if you want, I think the link for this paper is also sent by Fatima. And if you want more information about this type of research, there are very good references at the end of the paper that talks about other publications. If there are no questions, thank you very much, everyone, for joining, and hope to see you soon. Should we stop recording? Can I stop recording?